Добрый день.
Добрый день.
Что-то как-то вообще
Может,
никого нет. Даже
может, мы
странно.
объявление не разослали? Я что-то сейчас не могу понять.
Шень послал видеозапись. Да, а объявления, кстати, не было. Опс.
Это прокол.
Да уж. Я разослал объявление по Вышкинскому этому самому. Там есть телеграм-группа, ну вот для НИСа. И туда я вставил объявление, что будет продолжение семинара. Но при этом я почему-то был, ну правильно, я просто на это письмо Шиня только сейчас посмотрел, что там и ссылки нет, ну то есть там только про видео. Да.
Нет, ну да, как-то
Давайте,
это...
давайте посмотрим, как оно будет. Может, все-таки кто-то подсоединится. Странно, конечно. Ну, странно, что того же Шиня нет. Я подозреваю, что даже...
Нет, он прям будет, по идее.
Ну, давайте хотя бы его дождемся. Может, будем решать, что делать. Да, это действительно прокол как-то вот... Ну да, вот в форумах у меня нет других писем. То есть у меня есть письмо про 16 и вот это вот письмо про видеозапись. А я его, по-видимому, воспринял как объявление о следующем семинаре.
Я как-то тоже так воспринял, да, что-то у меня...
Знаешь, когда я писал в эту группу НИСа, я даже не стал ссылку копировать. Ну, там просто было предыдущее. Я написал, что по той же ссылке, там в то же время. Что, может, кто-нибудь и припрется. Хотя, по-моему, в прошлый раз нет. Был один парень, да, из НИСа, точно. Они тут у меня писали тест. Вот кто-то еще подсоединился. Интересно, кто? Опс.
Добрый вечер, это я.
Добрый вечер.
Это вы, это кто? Артем.
Да.
Вы почему-то изобразились у меня кракозябрами.
Да, я вижу, да, сейчас я переименуюсь, я тоже не понял, почему так случилось.
Все, теперь нормально.
Ага, и Шень появился.
Ну, мне было, правда, не очевидно, куда заходить, потому что, ну, я догадался, что...
А я ж вроде бы
надо
написал в чат НИСа, что по той же ссылке.
по той же? А я пока не
Нет,
вижу.
ну это да, это мы прокололись.
Мгм.
Ну, я прокололся, что я что-то как-то не разослал объявление,
Да все
что не
мы как-то
послал
вот...
видео, и я как-то предположил, что он же там и как-то написал про следующий семинар, но я не хочу возлагать всю ответственность на Шеня. Я сам виноват,
Да
так
все
сказать, во
виноваты,
всем.
чего ж тут сказать. Э,
На сайте семинара я выложил объявление.
ну то есть самые такие...
Да, это верно.
Самые крутые должны были все
Ну,
равно увидеть.
я следил за группой в Гугле, там не было, то есть только на сайте. видел.
Да.
Нет, но можно сейчас прямо написать туда, что вот, значит, пока не поздно, давайте.
Можно и написать,
Сейчас
наверное,
я-
не знаю.
Напишите, пожалуйста.
Еще кто-то подсоединился. Ну правильно, это те, кому я написал. Я-то в объявлении НИСа написал, и народ подсоединяется.
Вот, ну я отправил, смотрите, получили вы?
Сейчас посмотрим.
Ну.
Да, получил.
Да, есть письмо.
Да, ты, правда, написал очень коротко, и совершенно непонятно, когда мы будем пробовать еще раз слушать.
Ё-моё, сейчас я исправлю.
Самое главное, где мы будем пробовать.
Так. Мне до сих пор не приходит письмо. Но это моя почта такая просто.
Там очень хорошо фильтруется спам, вероятно.
Да.
Ну, мне одно пришло.
Да, нет, ну сейчас я хочу списать копию.
Сейчас я
Доступа
попробую
послать в ссылку.
самое расшарить. Сука, что-то.
Да, started screen sharing. Да.
Так. Как бы мне сделать еще всякие камеры, чтобы они шли.
В смысле?
Нет, но можно сделать изображение с планшета, а камеру с компьютера.
Ну, мы экран
И
сейчас видим.
Экран видим. Лигра анонима сехаунида, сообщают нам. И сейчас я даже посмотрю, могу ли я что-нибудь написать.
сейчас надо Apple TV выбрать.
Могу.
So I'm on page 10.
We see this. As you guess. But strangely, I can see only 4 participants among 10. Don't know why.
All right. I mean, I can just. So it's true that it's not. I do not assume that you remember anything from the last time.
So it's just a second take.
It's a second attempt. Yeah.
Yeah. Дубль второй. In Russian, it's okay.
Second pancake.
A blind. You don't.
Yeah, so at least my plan is to is to start with this description of the Lempel Ziv algorithm itself. And probably I will manage to do that, at least the description. And then the plan is to state something that can be proved about it. But then the other thing is to prove it. So
Well, state without proving is better than proving without stating. So let's try.
yeah. So probably let's start. So the first thing that I want to do is to describe the Lempel Ziv algorithm.
Actually,
Well,
it's one of
just
two Lempel Ziv algorithms. There is something known as Lempel Ziv some 1 year and some other year. But it's probably the most well-known, the simplest.
yeah. So a Lempel Ziv algorithm. So, well, it's supposed to be a compression algorithm. So this would be a function from binary strings to binary strings which is injective. So this means that we have a string X, we apply the algorithm to it, and the resulting string we want it to be, have of smaller length, but since it's injective, we will be able to get X back from LZ of X. So that's the idea.
If we lived in
And
medieval times, when everyone published his invention in a short phrase, with letters exchanged, I think the patent could be cut X into different pieces. This is what should be patented.
Yeah. And okay. And this transformation, both of the it will be encoding, and this will be decoding, and more or less both these transformations can be done in polynomial time. I think even in like time O of n log n, where n is the length of X. So let's describe LZ of X. So description of LZ. So it starts, so it receives X of length, a binary string of length n, and it starts by splitting it into subwords. So in the end, we get a representation of X as a concatenation of m subwords, and so what's the rule? And then we will. It's a preprocessing step somehow. So what's the definition? So there is an inductive definition of xi, and xi I let to be the first prefix. So we assume that we already constructed x1, x2, xi minus 1. Yeah, and also let's, for notations, define x0 to be the empty word. So xi is the first prefix after x1, xi minus 1, such that, well, which differs from all the previous blocks, and it's not empty. From. So so it differs from x0 so it's not empty, so it's something, and then it differs from all the previous constructed blocks. So for example, I don't know, if I have 0, 1, let's consider x that goes like something like that. 0, 1.
Sasha, wait a sec.
Yeah.
It's possible that there is no such prefix at all.
Yeah, that's
No,
possible.
we get a non-incomplete last block, but this is another story.
So let's say if there is no such prefix, prefix exists, then we set xi to be just the rest of x. And then the number of blocks is this
should be,
I.
we should remember about it. But
Yeah, so just an example how it works.
Picture like this. So we have a binary tree, and then we have a sequence, and we cut the sequence into some pieces and mark these pieces in a binary tree, empty piece, some 0 or 0, 0 or something. So we have some subtree, and the new piece is the first place
when the rest of the sequence goes out this tree. So without the last letter, it's still, it existed before, and with last letter, it's new.
Yeah, and some books, they use general input alphabet and assume that the last symbol is a symbol that's not used anywhere else in the string. So to avoid this last case.
Okay,
Yeah.
Then we get some bounds in terms of alphabet bound becomes a bit.
Yeah.
Whether we should do it or not.
Yeah. So the only, so let's assume for simplicity that we encode binary words also.
Does anyone know whether it's LZ77 or 78? Maybe someone just remembers this. I remember there are 2 years, I guess, 77 and 78.
I've written a paper 8 years ago, and it was important. There's different. It had to do something with how to encode the last bit of the tree, but I forgot everything. I'm sorry.
Okay, so you confirm that this is Lempel Ziv, but do not know which year.
Yeah.
Yeah, good.
But for the theory, it's not important. It just in practice, one works a little bit better.
Okay.
All right. So I just wanted to give an example how we produce these X strings. So let's say we have this, and initially X0 is empty. So we start from the left, and we take the first prefix which differs from the empty word. So it's always will be just the first letter. And now X1 is 0, right? We have constructed X1. Then we try to construct X2. So we now start from here, right? We take the first prefix which differs from X0. Well, so that means that it's not empty. And from X1, which is 0. Well, 1 works. Just the second letter works. And then X2 will be 1. All right. And then now I'm in a state. So I constructed X1, X2. I'm constructing X3. Now, well, so I take the prefix which differs from empty, 0, and 1. Well, 0 doesn't work because it coincides with 0, so I have to take 0, 1. And X3 will be 0, 1. And the same, and we are lucky now that, well, it's not lucky, it's just happened so far that now X4, well, it will be now 0, 1. Okay.
Now the test question, whether people understand how it works. So what are the cases when blocks grow fast and blocks grow slowly? Just informally, what are these two cases? Can anyone say this except Sasha? What is the string which is cut into big blocks and into small blocks?
Yeah, I guess we can. So this example that I just took is just you can continue it.
Let people say they are. If they don't understand that something is wrong here, we should stop. So let someone.
I wanted to give a hint.
No. For this, no one needs a hint.
But maybe the question is not clear.
No, if question is not clear, then they should say this. Okay.
They grow slow if you take all the bits first, 0, 1, then all 2-bit sequences 0, 0, 0, 1, 1, 0, and 1, 1, and then all 3-bit sequences and so on, I guess.
And so the length is more or less logarithm of the number of the block. Okay, this is slow growth and fast growth. What is the example of fast growth?
All zeros, I guess.
And then the length is growing linearly. And if we have n-bit strings, we have square root of n blocks, more or less, with size from 1 to square root of n.
Right.
So the blocks can grow in different speed, but still not very slow and not very fast.
Yeah. But okay, so we're at the step when the algorithm obtained this partition.
Now maybe somebody explains how to encode this. Imagine we make the splitting. Then we need to encode the blocks. Do you have some suggestions?
Well, I guess we need just for every xi, we do not need to write xi explicitly, but we know that xi has the last letter, and its xi without the last letter is already among factors. And we need to specify the number of that factor and also the new bit, I guess.
So for block numbers n, number k, how many bits you need?
Log k
plus constant, because we need
plus 1.
Yeah. And it is it is prefix code. Why it's prefix code? Just say it.
Because we want to concatenate all of them, all these numbers. But if we take prefix-free encoding, we will increase the length. We increase the length by log.
No, we don't need this, because if we encode, if we now are on the ith block, then both in decoding and encoding, you know I. So you need just reserve log I bits for the number, and if the number is small, many of them will be unused. But that's okay. And then you know when the number of the number of one of the previous block ends, and then you don't need any overhead for the splitting.
Yeah, let me repeat it, and I mean, writing something meanwhile for everybody. So yeah, so we notice that the kth block that we have, unless it's the last block, maybe it's some previous block xj plus some letter, right? Because it was the first, so we obtain xk when it was the first prefix which differs from all the previous ones. But right before that, it wasn't so. So right before that, this prefix was xj for some j from 0 to k minus 1. And then we have a letter b, and then we have just one bit b. So therefore, we will encode the kth block with the binary representation of this j
aligned to log k bits.
And let's assume that so j is from 0 to k minus 1. So there are k options, and I'm using exactly log k bits for that, rounded up, plus b, which just, you know,
Plus
written.
one.
Yeah, I mean, the encoding of xk is the binary representation of j followed by b. And in the binary representation of j, we use exactly log k bits. Then, for example, for the Rust word, it depends. So if it was obtained in the same way as the usual, as the previous words, then we do the same encoding. If it coincides with one of the previous words, because we didn't find a prefix that differs from all the previous words, we can just encode it as, we can just use this first part for it. And then the encoding of the whole word is just a simple concatenation of all the encodings of these blocks. Yeah, but then we have to show that it's injective, right? So given a code, so okay, let me try
But
to.
maybe
So
everyone
the
already understands this. Can anyone explain why it's injective?
yeah. So let me just, I'll just say that. So I define the encoding of xk, and I define encoding of x as just a simple concatenation of all these encodings of the blocks. And the claim is that it's injective. So given these encodings, we have to reconstruct x1, xm.
Well, we can, I think, just the contradiction use. So let's suppose that we have some two different words for which we have equal encodings, and if so, then we should have for some bit the situation for which for two different bits we have the same encoding, and it seems like it's not possible because of our just definition of encoding.
No, you don't really say much because you repeat the statement, but it's so obvious that it's probably the only thing. Just the reverse decoding is quite clear. We know how many bits to read, then we know which block to take, and then we'll know which bit to add. So decoding is obvious. Yeah.
Yeah, so we go just from, we want to decode x1, xm, one by one. So once we have reconstructed x1, x2, xi minus 1, we need to reconstruct xi. And so we have this encoding of xi. We know that exactly the first log I bits of it encode the index of one of the previous words with which xi starts, and then the next bit encodes the last bit of xi. And in the case when we have just log I bits and nothing else, we know that we are in the end of the word, so it's the last block. So we just define xm is the letter with this block, one of the previous blocks with this index, and that's it. Yes. Okay.
So there exists a variant where this second bit, you don't need to encode it, but you use it as the first bit of the next sequence that you encode. And this is a small improvement in practice but for the theorem it doesn't.
Say it again, Bruno. Say it again.
So so every sequence is encoded as a pair, index of the previous sequence and the next bit. And then there is a variant where you don't encode this next bit, but you use it as the first bit of the next sequence. So then there is not this nice decomposition as a prefix-free string. Yeah, and in practice it works a little bit better, but I've forgotten how this variant is called. And so, yes, and we used the second variant in a paper with Attila, but the goal was not to do compression, but it was for some machine learning problem.
Okay, but I think it will make the analysis much worse, because now every block more or less is it already was before.
Yeah, and the proof so the analysis is much worse, but the result is the same, because it gets included in the big O notation.
Yeah, so in the end, what we have is that the length of the code is, if I have m blocks, length of the encoding will be something like so for the first block we use log 1 bits plus 1, for the second this, and I don't know, for the last one we use log m plus 1 at most, maybe even without this one. But this is okay, so this is just m log m plus small o of m, because, well, it's so we have these things that ones that are m of them, and then we have the sum of logs, which is log of the m factorial, and this is more or less this, which is m log m plus O of m.
In fact, you even don't need this, but okay.
Yeah. So, and it's also more or less clear that all this encoding and decoding can be done in polynomial time, even like in linear time, more or less. Like encoding, you have to keep the list of the words that you have already constructed, then you go consider larger and larger prefix, and each time you ask whether this prefix already exists in a set of words that you have already constructed. Well, if you can keep them ordered in some way, you can do this like in log n iterations, then you have more or less n log n. But okay, polynomial time definitely. Okay, and then we want to, okay, that was the first part, the description of
about the algorithm. So assume that without we change the algorithm. Instead of taking the longest prefix, which is absent among x1, xi minus 1, we take the largest word which has the form xk plus 1 bit. Will it be the same algorithm or a different one?
the largest one.
So yes, the idea is to put as much as possible in the current factor xi, right?
No, it's the same, because imagine we apply standard algorithm. Imagine they coincide up to some point. Then you take the new algorithm. One way is to take the first prefix, which is not in the subtree, and the other is you take the maximal prefix, which is in subtree. So this is the same thing. So at any point we have a subtree. If we have a prefix, a string in a block, then all prefixes appear early.
Sasha, so we need to prove a lemma. Then all the factors form a subtree, right?
Yeah, because if you take a subtree and add a minimal thing outside the subtree, of course, you just extend one vertex.
Okay, so we have
Yeah.
and then
So it's a subtree, and then
okay.
what Sasha says is you take the first place outside of the subtree along the path.
Right.
And you say you take the maximal place in the subtree along the path and add one bit. As
Yeah.
somehow by definition or by simple observation, it's the same.
Okay. I got it.
Yeah. And what is the most probably only important thing of this encoding is that all the blocks are different. This is a very important thing. More or less.
Yeah, except
only property.
The last one.
Yeah. The last one is forget about it. But it's the only property we need about this code. If there is any other way of split this thing into different strings, which will be encoded as efficiently, then everything will be okay.
Yeah, let me state so now we are going to show a theorem that some upper bounds on the length of the encoding, and for these upper bounds, yeah, indeed it will be only important that all the blocks except possibly the last one are different. So let's try to state some theorem. Yeah, so I want to try to state the theorem so the upper bound on the length of Lempel Ziv encoding in terms of entropies of blocks. But then we'll see how it works. So let me try to state. So for all k, for all n, and for all words of length n, we have that, okay, so I have a word x, I take the Lempel Ziv encoding and I'm interested in its length. So I'm claiming that I can upper bound it by as follows. So I take entropy of something, that will be the entropy of k length blocks divided by k plus small o of 1 times n. So what is pk? Pk, it will be a probability distribution over k bit binary words. Produced, so how it's defined? So we take x and we divide it into disjoint blocks of length k. And then we let the probability of some binary word of length 0 of length k to be the fraction of times it appears in this partition. So pk is a probability distribution over 0, 1 to the k produced by the partition of x into disjoint blocks of length k.
And what if we can't divide our x on disjoint blocks of length k, or it's less or equal than k?
No, one should say more
Well-
exactly what is small o of 1, because there is a natural question. Imagine that we take just k is equal to length to x, since theoretically it's not forbidden. So then the entropy is 0, and so we get something like o small o of 1 times n, which is of course impossible for arbitrary x. So small o of 1 should be understood in a very clear. One should explain.
So small o of 1 is the function of the n.
So
It's some function of n
it
that goes
on
to
k,
it depends on k, yes.
but not on
But for a
x.
fixed k, when you increase the input length, this function goes to 0.
So you just should write index subscript k near o, so it will be clear that it depends only on k.
Yeah, we can write it. I mean, let's write it without any. So not to have any doubts. There will be some function there such that f of k n goes to 0 when n goes to infinity.
So a regime which is
So-
interesting for us is k is fixed, and then we take more and more longer strings. But also what is important that it's any string. So for different strings, we can have different frequencies, entropies. So we don't assume that they have some fixed distribution, but fk doesn't depend on the distribution, only on k.
But do we have any formula for that function? Maybe
So-
it would be clear if we have just a formula.
No, I think it's something like constant divided by k plus a number of blocks plus.
I think we can obtain something like that. K divided by square root of log n plus 1
over k, a constant over
1 over log n. But maybe this is already, yeah, so this is worse than this. So just like that. That one we can obtain. But that, I mean, just the version with
No,
this.
there should be some element, also 1 over k, because it's because of Hamming overhead. It's
1 over k I don't like because it doesn't go to 0 when n goes to infinity. Then it would contradict what I just wrote.
okay, yeah, it's k is for bigger blocks, yeah. No, actually, there is two. When you prove the theorem, the first step is just choose some size of bigger blocks, and then you need to adjust the size of bigger blocks to compensate different objects in different ways. But
Yeah, so I will try to prove at least this version where I don't specify fk of n. I just want to show that this is 0, 1, small o of 1 as a function of n, but the specific function of n can depend on k. Who? Yeah. Okay. So let's try to. So other questions about the statement. Yeah. So right. So now, yeah. So now I want to reformulate it, just basically give a definition of the limit. So I want to state another version that implies it, is that for every k and for every epsilon, for all sufficiently large n and all x's of length n, we have this bound up to epsilon. So the Lempel Ziv code of x is bounded by this entropy plus epsilon times n. Well, it's just the definition of the limit that this overhead goes to 0 as n goes to infinity. All right. So for the proof, we can assume that we have this k and we have this epsilon. And whenever, I don't know, I write, for example, that something exists, it may depend on k and epsilon actually. All right. Maybe I can copy the statement.
You can copy the page and then erase what you don't need. There is a simple trick also.
Okay, I guess it's easier to just, for example, erase this and start proving it. So, and there are two major steps in this argument. So the first step, we need to construct a complexity function, which is, so we need to just construct some function C from binary words to natural numbers. So this function C provides every binary word, assigns every binary word some natural number n that we could call like C complexity of this word. C of some word A is C complexity. And we need three properties of this C. The first property is that it's superadditive. So if I take complexity of concatenation, this is at least as the sum of complexities of the words we have for all A and B. Then I need the property that saying that if I'm interested in the number of words that have C complexity at most something, it shouldn't, there has to, basically there has to be a low number of words with low complexity. More precisely, there has to exist some constant f such that for every, I don't know, t, the number of words with C complexity at most t doesn't exceed f times 2 to the t. For example, if we imagined that t is a Kolmogorov complexity, which is not superadditive, but still, then we would have just this with 2 to the t. But for the argument, we need to allow some constant before 2 to the t. But this, yeah, will be this constant f will just depend on k and epsilon here, but it will be the same for all t. And finally, we need a third property, that C complexity of my word x is at most, this thing that I defined here. But maybe with, let's say, epsilon half times n. Yeah, so I have to classify. So C, the complexity function C, depends on x. We construct it in a specific way for it to have a low value on our word x. But this constant f doesn't depend on x. It just depends on k and epsilon. And then the second step is to show that the length of the Lempel Ziv encoding can be bounded from above by any function that satisfies the first and the second condition with some margin again. To show this. Is it most Cx plus, now I can even write this for every C that satisfies superadditivity and the second property for some constant f.
But then you should say whether the small o depends on f and how it depends on f, if it does.
Small o depends on f. But f itself depends only on k and epsilon. So then I finish the proof by taking just n, for which this small o of n, I mean it's the corresponding small o of o is smaller than epsilon over 2. So
okay, Koля, maybe you can, since I already heard this, maybe you can say whether it needs to be explained in more details, or it's clear, or because I'm a bit lost here in terms of what is clear and what is not.
It is becoming complicated now. Before, everything was clear, but now I guess the problem is that we introduce some function without any intuitive idea. Why do we introduce some function? As I understand from the last lecture, it's sort of a type 2 automatic complexity, something like that, right?
Yeah, let me just explain the general scheme in few sentences. So we can consider this if we have this compression with if we have some small entropy, then it gives some Huffman code, maybe with bigger blocks or whatever. But this Huffman code corresponds to a finite automaton, decoding finite automaton. And then we forget about the code and we consider how many actually to this decoding automaton for each decoding automaton we can construct a superadditive function, and then we apply that general result about superadditive functions that are bounded for Lempel Ziv code. This is the second step. So the only thing we need to know about the automatic complexity for this automaton is just that it's superadditive.
So I guess that it will be easier to understand if we just forget about first step and also forget the theorem and just prove that the statement of the second step, that any superadditive function with that combinatorial restriction, I mean the second one, is an upper bound for Lempel Ziv. This is easy to understand, and the rest will be just the corollary of this main result, as I understand, right?
Yes. Corollary where you have to say something still, but so they what's the point of this superadditive function? So let's try to show the second step. So or even forgetting about the statement of the theorem, we just need to show the upper bound on Lempel Ziv complexity in terms of any superadditive function.
Yes. I did understand this, that given also the previous lecture, we understand everything, right?
Yeah. Well, if we understand previous.
Yeah, assuming that. But still,
the
new stuff is this second step, right?
Yeah. So the new stuff is the second step.
To the second step and forget about the theorem and the first step.
For a while.
Yeah.
For a while, right.
So the point is that we are now where we are. We are proving the second step.
And in the second step, the function which is little o of n depends only on the constant f. It doesn't depend on c of x, right?
Well, yeah, it doesn't depend on c.
That's interesting.
Yeah, so well, this step is like where we're using the fact that x is in the Lempel Ziv encoding is partitioned into different blocks except the last one.
Yeah, let me say one sentence. So since x is partitioned to different blocks, we can get a lower bound for c of x by the sum of complexities of blocks. C complexities of blocks. So the question is why the sum of the C complexity cannot be small. And
because the blocks are different,
because the blocks are different, and we cannot have too many things with small complexity.
Right.
That's all. And this is why this Sasha's argument is wonderfully simple. So now you can present in complicated way.
Yeah, so our goal is to show that C of x cannot be much smaller than the Lempel Ziv. That's the plan. Okay. Well, since it's superadditive, it's at least the sum of our complexity of our blocks. And except even if we forget about the last block, this is the sum of m-1 of my complexity on m-1 different blocks, different words. Okay, my goal is to show that it's not so small. Well, I have m-1 different words, and I know that my complexity is small for a small number of words. This means that most of these m-1 different words have big complexity. And then, okay, then there is, yeah, so, yeah?
Yeah. So just let me again say one sentence. So we have this
Yeah.
complexity of blocks, and we want to show that it cannot be small. Let's minimize this complexity, assuming that the only restriction that we have at one most string of complexity 0, at most 2 strings of complexity 1, at least 4 strings of complexity 2, and so on. Forget about constant f for a while. Then, of course, the minimal sum will be obtained. We will get 1, 0 plus 1 plus 1 plus 2 plus 2 plus 2 plus 2 plus 4 plus, and so this is the minimal possible thing. And the minimal possible things, if you look at the sequence, it's exactly logarithm 1 plus logarithm 2 plus logarithm 3 plus so on. And this is exactly what we get for Lempel Ziv. That's more or less all.
Sasha, it's not clear.
What is not clear?
Why do we sum logarithm? I don't see.
No. We just look at the sequence. Okay, let's go in another direction. Consider sequence: logarithm 1, logarithm 2, logarithm 4,
Right.
logarithm 5, and they take
So how many logarithms we sum up?
just let's consider infinite sequence. Let's look what is the sequence. Log 1 is 0. Log 2 is 1, and log 3 is 1. And log 4 is 2, and then we still have 4 numbers like 2, and log 8 is finally 4. So
wherever we stop, we just stop in the same sequence. As we did in Lempel Ziv, there was additional one bit only, and maybe one more bit because of upper bound for logarithm. So if we don't have the problem with this constant number of factor f, we get exactly what we need. And if we have this constant factor, we can, at that moment, we can increase the value of complexity by logarithm f, and so reduce this constant factor to 1. That's more or less all the reasoning needed to see this. I don't know whether this explanation is clear, or maybe indeed it's better to now provide more formal one.
So in this argument, we obtain just an inequality without any error terms, right? Where
yeah, I'm not sure.
Yes, but we assume that there are at most 2 to the power t words of complexity t. But we have a weaker assumption.
f times power of 2.
Yeah.
So we have f to the t. We should
replace by f to the t.
Okay.
And then after
No, so we need to use superadditivity, but after using superadditivity, we increase C by log F.
In this way, we decrease the number of no, we just change the scale a bit, and then we get at most 2 to the t object of new complexity at most something. Just if we change complexity by a constant, logarithmic constant, is just the number of objects with this complexity is multiplied by f. That's one thing. Another thing is we need to comparing this and this, comparing this and Lempel Ziv. We should remember that Lempel Ziv gives log I upper bound +1, so we need add 2 per block. So we still need some kind of overhead. And if I'm maybe I overlook something, but it seems to me that the only sources of the overhead here.
So the error is proportional to the number to n, as I see, right?
No,
To the number of
error
blocks.
is F plus O of 1 times of the number of Lempel Ziv blocks.
Which is not n,
as we
it
know.
is m.
No. N is the number, is the length of strings. And we know the length of blocks. We, as you
in the first line, then change n to m in the first line on the slide. Okay.
So number of blocks is bounded by n log m, because we agreed,
especially you in the beginning, that the blocks are of size log n approximately. So the number of blocks is more or less n divided by logarithm n. The average size of block is logarithmic.
Oh, there is constant some fixed constant.
And so it is much smaller than n. So this term is still O of n, small o of n, as requested in the theorem.
And please say it again, why this is the upper bound for the number of blocks?
We are interested in the number of blocks, in the n divided by the number of blocks.
Right.
Which is the average length of block.
Right.
And so, and all the blocks are different. So the minimal total length will happen if they are all fill the bottom of the full binary tree. And then the average length of such a blocks, most of them are on the highest level, the half of on the highest level. So average is about log n omega of log n.
And so the number of blocks is n divided by log n. Okay, so what people think should is it clear, or it should be explained seriously with formulas?
I'm afraid that we won't understand it better with formulas. Now it's sort of clear, at least I have such an impression. Maybe a wrong one.
But there are a lot of formulas on the board. I don't understand why this explanation is called explanation without formulas.
For that, you should hear the other explanation.
But what happened? Why the board stopped being showed?
But who's sharing the blackboard?
Sasha, who was sharing the board.
And it seems like he isn't in.
Sasha disappeared. That's the problem.
Okay, but then you cannot get an explanation with formulas, but you can ask something about this this explanation. So we used indeed several times the idea of getting lower bound, comparing what will happen if we will minimize this. For example, if we have different binary strings, what is the minimal total length, average length of them? And of course, we should take the strings of the minimal possible length. So we should use the binary tree from bottom to top. And also, if we want to estimate the sum, of course, if we know that there are the only restriction is that the number of small terms is bounded, of course, we should use as small terms as possible. We should fully use the smallest possible term, the second possible term, and so on. Every other thing we can improve by exchanging a complicated string by a simple one, if it doesn't, by decreasing some complexity, if it doesn't violate the restriction of the number of simple strings.
I have a side question, maybe while Sasha attempts to connect again. Sasha is here.
Yeah, I lost connection.
Yeah, so
sorry.
then you should.
My question is very simple. Is this version of Lempel Ziv is used by some real practice programs? Say Zip. Zip uses some version of Lempel Ziv, but is this exactly this version?
No, actually, Zip as a program, Zip, actually commercial program Zip, uses several different types of encodings. So definitely they use something more than not only this version. And whether it's one of them, one should check. I'll try to see.
I'm satisfied. We can continue. Sasha is now online.
But I don't know what to do. Basically, we finished the theorem, right? And then.
No, we finished the second part.
Or I can try to explain again how to construct this superadditive function from entropy.
Without automaton?
No, with
does it?
Of course, without
does it make sense?
But one should at least name the main steps.
Yeah. So let's. So our goal is to construct the superadditive function. And this superadditive function with this some constant.
More or less achieve the entropy bound with some small terms.
Yeah, and then it's also the number of y with c, y complexity is at most t. And it achieves this entropy bound. The idea is that we will first construct a finite automata that we will consider this finite automata as a decompressor. With the property that this finite automata, if you define like Kolmogorov complexity, so the minimal length of our word x with respect to this decompressor will be at most this entropy bound. Some epsilon 2. And well, and then we want first two things that, and this finite automata, we assume that works as follows. It reads its, an input word, and also it can either read an input word or it can output one word at the time. May either read an input word or output some, read an input letter and output an input letter, but one at a time. In one unit of time, it can do one of two things. And we also want that the number of states in this automata should be some constant that depends on our k and epsilon. And then we define but it's not superadditive. Well, at least it's not clear why just the Kolmogorov complexity with respect to this finite automata is superadditive, but it's superadditive if we define the C of W as the minimum also over all states of Q. So, well, this automata has some initial state, but let's assume that we can minimize also, we can change the initial state to any state of the automata, and then to be the minimal overall y, length of y, such that CA, if we run our automata from Q on y, it gives W. So now so basically we are minimizing, we have not one decompressor, which is this automata, but constantly many of them, at most at most that many as there are number of states in A. And so basically this F will be now the number of states, the number of these decompressors, which is basically the number of states of in A. Yeah, and why it will be superadditive? Because if I have some description for W and then I split it into two words, then in this description for W, there is the first moment that after which we obtain W1. And then automata is in one of the states, and from this one of the states, the rest of the description of W produces W2. So from the description of W, we can split it into two descriptions, one for W1 and one for W2. And then possibly even for W1 and W2 themselves, we can have shorter descriptions. And then we obtain this. And now the main thing is to construct, what remains is to construct an automata that achieves this entropy bound with this precision. So I don't know. So what I just said, was it clear or no? And what remains is to construct an automata that achieves the entropy bound with finitely many states for a given k and epsilon.
So one can say that, of course, the Kolmogorov complexity is not superadditive because complexity of AA is not twice complexity of A. But if the memory is local, if the algorithm has only finite memory, then somehow the difference is not big because just we cannot remember much of A. And formally it said like this. So we may assume that our decompressor is a finite automaton. And then still maybe this exactly the inequality is not true. But then we replace our complexity by the minimum taken over all states of automaton. Then it becomes true, because if there is short description which produced A, B starting from some state, then some part of this description is producing A, and the rest is producing B, starting maybe from some other state, because we started, A moves us somewhere. So the only thing is needed, we should produce string only one bit at a time, going in a new state, producing only one bit.
Yeah.
And then we pay, because now we have more descriptions, because actually each smaller complexity, because now each description may be used for several strings if started from different automata states. But still it doesn't matter much, because the number of states is a constant, so we get only constantly more bound. This is the reason of why we have F. So is it clear or not? Kolya or Bruno, just say something.
It is.
Well, I'm a bit confused about dependency of F on K, but since we didn't construct this automata, we don't know it yet.
Construct automata. No, actually, if we have an automaton, we need to estimate. It's important to estimate the number of states and understand on what it depends.
Yeah. So let's try to discuss how the idea is that, okay, we have these blocks, and I want to
of some given size k, small k, some k.
Yeah, size k.
Yeah.
So, and in my compressed version, I want to use some prefix-free code for words of length k, so that every block will be replaced by its coding in this prefix-free code.
No. First, you need to switch to bigger blocks. If you want to.
Well, let's discuss first the small blocks, right? So what we will obtain if we will just use
if we use prefix code for small
prefix-free
blocks.
code for the blocks that we have. First of all, for block U, I wanted to be encoded. So we have this distribution of the blocks, and I wanted to be encoded by at most log 1 of the probability of this block, at most plus 1. We know that if I have a probability distribution, then there is a code, Shannon's code, where the length of the word, if the probability of the word is p, the length of the code is log 1 over p plus at most 1. Right? And then if I will use this encoding, every block, so if I have, what will be the contribution of every block into the length of the compressed version? So the length is log 1 over k plus u plus at most 1. And it will appear how many times? Pk, the probability times the number of blocks. That's how many times we have u in our n over k blocks. Then you see, if you sum up overall u, we have n over k, we have entropy of pk plus 1. Which is, okay, this is like n entropy divided by k plus 1 over k.
So this is called Shannon Shannon encoding theorem.
So, well, the problem that we will have is that we want this to be smaller than 1 over k. We want it to be epsilon, which can be possibly smaller. But okay, let's discuss that. But we need some constant number of states that depends just on k and not on the word and not on the distribution p. I'm saying that I can do that more or less with something like 2 to the O of k states, dependent on everything. Why? Because, well, how my automata will work? Basically, it will receive some prefix-free coding. I mean, encoding of one of the code words in my prefix-free code. It will just read it until it sees that it is a prefix-free code in my code, and then it understands what it encodes, what is this code for, and it outputs k letters one by one,
So
which
the automata
block
has
of
two
like
stages.
k.
First, it goes up the tree, up the code tree, and until it found the code word of a prefix code, and then it produces it goes to zero to the root on the way, producing one by one all the bits.
Yeah. So basically, so for the first step to read the prefix-free the code word, we need so we have our prefix-free code. We can write it as a tree, right? Where leaves are code words. And we basically have to have the number of states, which is equal to the number of nodes in this tree. So there is a problem, right? Because we don't know anything about the probability. In a sense that I'm saying that the length of
can be extremely small.
Extremely small, and then the code word will be big. But what I can say here is this trick. So I have a tree, and there are 2 to the k leaves, right? Because there are 2 to the k code words. If this tree were binary, I mean, if every node has 2 children, right? We know that then the number of nodes, so the number of inner nodes is at most the number of leaves. So if this tree were binary, then we could say that the number of nodes in this tree is at most 2 to the k times 2. I don't know. But the problem is that, well, in principle, it could be that there are parts like that in the tree, right? But why do we need them? Let's just if we just merge these parts where a node doesn't have any children, it's still a prefix-free code, right? And the length of the code words just becomes smaller. And
Yeah,
it
but
cannot
formally-
become bigger.
Code tree cannot have vertices without splitting, because otherwise it can be optimized by just deleting the edge.
Yeah, but still you
Yeah.
need to print a string, and in your model to be formal, there might be there might be a problem
for
because
each vertex, for each code word, you need k vertices on the way back. So we should multiply 2 to the k by k.
Yeah.
We'll
multiply it to the k by k.
Oh, sorry. Yeah. Okay.
There's O of k in the export, so it's much more rough.
Okay, but now I forgot a little bit. So I assume that f was a constant that doesn't depend on k, and when we say that step 1 and step 2 imply the theorem, but now f
No, it depends on k. It depends on k, of course. But this just results that in the theorem, this error depends on k.
Yeah, but n was taken large. Okay, yeah, I remember.
Yeah.
Sorry.
So
Yeah,
now,
okay.
if we don't do anything else, we get something which is not yet the theorem, because we have entropy per bit in the optimal. We have error per bit about 1 over k, when k is a number in the block length. And in the theorem, we did not have this overhead, which is fixed for a length for blocks or fixed length. And the solution is that we switch to blocks of longer length, and entropy can only decrease, but then we pay more because we have more things in automaton. This f becomes bigger, the number of states become bigger. So we need to make some balance. If we take
we increase the block length, but automaton,
then overhead of 1 over k is important. If we make them too long, for example, we consider all the sequence as one big block, then of course entropy is 0. But then automata is very big, and you don't get anything reasonable because of that. So for the correct order, you should first increase the new block length, so to make this overhead over 1 over k smaller. Probably for that was epsilon over 2, as I guess correctly. And then another epsilon over 2, you should take length long enough that even this bigger automaton, which is obtained for a fixed block meta block size, is still small enough to disappear there. This is more or less the order of changing of choosing things, but I don't know whether it's probably confusing.
But I just think there is an easier way to understand, because in the second step, we have to pay log f divided by k for the states.
For the where
yeah,
k,
but if we do several blocks, then the number of states increases linear in the number of blocks, and then there is no problem. So now the automata is exponential in k, but when we repeat the number of blocks, we get something. We just have to copy the automata several times, so the number of states increases linear in the number of blocks.
No. When we increase the blocks, automaton becomes much more bigger, because if we take bigger blocks, we take a Hamming code or Shannon code for much larger alphabet.
Yeah, for the blocks of well, if I increase it, 1,000 times, then I will have to have a prefix recode for
you do not
blocks of length 1,000k.
by 1,000, but you just
yeah, it's an exponent. The 1,000 comes into the exponent.
So my issue is when we combine step 1 and step 2 into the theorem. Maybe you can go back to the slide.
Yes.
Okay,
so f depends only on k and epsilon.
Yeah.
And then this error here depends just on f.
Okay, let me try to say. So we have given k and epsilon. And then there is a problem of Hamming overhead of size 1 over k per bit. To solve this, we make this overhead smaller than epsilon by increasing the k. For example, we make this overhead smaller than epsilon over 2. Then we get some block size which is bigger, but it doesn't depend on n, because we just want 1 over k be smaller than epsilon. So n is not important now. So when we choose the macro block size, we take only into account epsilon and k. Well, epsilon actually. We need the macro block size to be of order 1 over epsilon.
Okay, I understand.
And then after that, this macro block size is fixed, and so the constant in this f constant f in our superadditive function is also fixed because the automaton is fixed. Not the automaton is fixed. The number of states in the automaton is fixed. Automaton would depend on the frequencies, of course, but the number of states in the automaton is now fixed, is bounded. And so even if it's large, still for large n, it doesn't matter. Because for larger n, we have big blocks, and the overhead, which happens because of this automaton big number of size is more or less proportional to the number of blocks. And number of blocks is small compared to n.
Yes. So the gain is a factor 1 over log n, and that just beating everything, any choice of gain.
Yeah,
and
of course. Then you can ask what is the best thing, the best choice of the macro block size when both errors are of the same order. So then you cannot improve things increasing or decreasing it.
Okay.
And I guess Sasha could confirm this, that this optimal size is 1 divided by square root of log n. Yeah?
Yeah.
But with
I
this
think
proof,
that's-
it's 1 over square root log n. And with the original proof that you check. So I haven't seen this proof.
No,
I
I
don't
can say something about the original proof. Meanwhile, I looked. First, it's LZ 78. This is not 77, but 78. This is the first observation. The second observation is that there is Lempel Ziv paper is more or less.
Yeah, but original proof is, it's like what Sasha presented. I'm not sure.
I think it was 1 over log n.
Well, it's
there was
inevitably
no
1 over
square
log
root.
n.
I think there was no square root, and it was better.
You mean optimal block size was better?
Yeah.
No. I mean, I'm not sure. They consider. I mean, it's 1 over log n possibly for constant size blocks, right? You
Yeah.
can make it.
Okay.
Or
So who
yeah.
of you have read the original paper? If any, just tell me. Is there anyone who tried to read the original paper?
I mean, the only
No,
thing I was
didn't.
reading is the original paper. I didn't take it from my head. So I
okay,
was reading it. But that doesn't mean that I can explain.
But you cannot even say which
what's
of the
written there.
original paper you read, right? So it's not that 77 or 78. But I found some reference, which is lecture notes of Goemans from MIT, which clearly says that Lempel Ziv is 78. And also that it contains some analysis, but analysis in this lecture notes, I think, is much less. It's not they consider the not a given string, but they assume a source, a randomized source. So they assume somehow limiting frequency and so on. But maybe, Bruno, if you can look at Lempel Ziv 78 and explain why it's better and what they do, it would be great.
And they're doing this in 78 in this paper.
They're doing
The
what?
argument is more or less like that.
Yeah, but
Do they say at some moment
that to get optimal
They
one,
actually, so as Bruno was mentioning, that there are some optimizations that work in practice, but this is like this, like the algorithm is just like this in their paper.
but
The
do they
argument is
achieve
that,
something about 1 over log n?
well, it depends. 1 over log n,
So
it's not really
what size
possible
of
when you
block
have
they
already
use?
blocks of,
If you have n-bit string, what block size they recommend?
they don't recommend any block size.
Okay, but maybe then Bruno can look.
They, in fact, well, I mean, first of all, Sasha, they don't consider entropy of blocks in their paper. They consider compression by automata with some number of states.
Ah, okay.
So they don't recommend any block sizes. That's one of the problems.
Okay, then we should look at this paper because
But
So
there is a book of Thomas, this famous book on information theory by Thomas and someone else, and they do it by direct computation, and it's kind of messy. And then there are people who write it more nicer. That's
Okay,
what I remember, but it was
but
a long
who are
time
these people
ago.
who write it nicer, and what do they write exactly?
Yeah, that's a question. And once I tried, yeah, and when I read it, I tried to explain to Sasha Shen, but I failed. And then there was something urgent.
What is the important ingredient is that we are explicitly saying that from a finite automaton, we switch to a superadditive function. And this additional splitting, I think makes proof much more structured. But maybe they already do it in hiding. But then it's
yeah, in Lempel Ziv there was the superadditive function, but not explicit.
Okay.
no.
They didn't say that they have a superadditive complexity function. It's just that we have an automata and we minimize what's on a given word. We minimize overall input states, what can be achieved on this on this word.
But do they explicitly say that the number of words which have description complexity of is bounded?
Yeah, they say it in the proof.
Yeah. Okay.
Well, I mean, how would you imagine it would go other way? It's just all, yeah, it's all there.
Well,
Yeah,
you can, for example, look in the Lempel Ziv notes by Goemans and see that it's not very clear.
well,
Okay,
I don't know how this.
Anyway, it's
Okay, but maybe I should read everything again and try to remember, and then have the discussion
if you can
offline.
spend I don't know half an hour trying to see what is in the paper and what they say and what they don't say, you probably are the best person because you already read and have a positive impression about that. But okay, so what do we have for the next time? Do we have some volunteers to give a talk? Where is Lyosha Milovanov? He is missing.
In Portugal, I guess.
Yeah, but he's missing. So we can decide that he will give a talk. But but no, maybe there are some volunteers which are here, especially some. It should not be something difficult. It should be your. It's not necessarily is your result. Just something nice and which will be interesting to many people.
So Artyom haven't ever delivered any talk. Artyom Parfenov, maybe you will volunteer.
Yeah, I'm not sure that I have much to talk to tell you.
But it's not today; it's in a week.
Yeah.
Okay.
don't-
But just I think you can discuss with Kolya whether it's okay, or maybe some other volunteers will appear.
Yeah,
So
we can discuss it, but just now I can't say anything about it.
Okay.
Yeah, I will be traveling. It's too difficult for me next week. But afterwards, I can maybe speak about one-bit probes. But Kolya and Viali already know this, but there were no proofs in
But
my
speak,
talk.
speak about what? Say it again.
This one-bit probe and this online matching.
Ah,
Yeah, and this connectors.
Yeah, it's a good idea to.
yeah, also announcement, unrelated announcement, that this week at Wednesday, Andrei Ramashenko asked me to deliver a tutorial talk about using compression argument to prove some combinatorial statement. Especially, he was asking me to look what is known about how it can be used to prime numbers. And indeed, there are some funny arguments. They don't provide anything really strong, but that's funny that there are several of them. And for example, there is an Euler theorem which says that the sum of 1 over prime numbers, the series of 1 over prime numbers, diverge. And you can usually you prove it using the infinite products and so on. And there is another very simple way to prove it, maybe even simpler than the original one, using kind of compression argument and complexity. So this it will be at 4:30, 5:30 Moscow time and 4:30 general time in Zoom and at the seminar of Andrei Ramashenko on information theory. So I can send an announcement if needed, because Andrei every time makes special Zoom session. So I think I have it somewhere.
And
Yeah,
is it recorded, this seminar?
yeah, it's recorded. Yeah.
Okay.
But
it
you
also
want-
sounds interesting, so it will be nice if you
Yeah,
send.
but Bruno, if you want to make fun of me, you need to be there. It's not possible to make fun of somebody when hearing his recording. So you are all the reasons to come.
Well, I will send pictures of my house I'm repairing, and you can make fun of me also then.
Oh, you will be at Wednesday. You will be already in
Yeah,
Belgium.
in Belgium, yeah.
No, probably in Turkey, not in Belgium. It's only 2 days. How can you come to in Belgium?
No, it's 24 hours to go to St. Petersburg, then Helsinki, then a flight to Belgium.
It's lower bound. Okay. Okay, so I will send the announcement, and feel free to come and
Okay.
if anyone, and it will be in English, of course. But yeah.
Okay, bye.
Bye.
Yeah. Bye.
Bye.
We should thank the speaker. After making fun of him, we should.
He's already gone, the speaker.
Yeah, but so
too late. Yeah.
we can thank him without his making fun.
Okay.
We need him, but for thinking, we can do it now. And
Yeah,
so,
okay.
no, I think it's a great thing. Even if Sasha says that everything is already there, I think it's a very structured structuring of the proof. It makes it better for explanations, makes it better for understanding, and probably gives something close to optimal. So if it's not optimal, it will be interesting to understand what kind of improvement we do not take into account here. Okay.
Bye.
Okay, bye.